Yeah, I was just.
Okay, so the stream is starting. Give it a minute.
Yeah, so now we can.
And then I'll let people in after that.
So yeah, let people in.
Excellent. Okay.
Sí, tenemos que.
Okay, so we are live. I'm going to start letting people in. And after a little bit, Melissa can do the presentation and letting everyone in.
Very good.
Okay, so it's 14:30, so we can start. Whether you can let people keep joining the meeting. Yeah. So thank you very much, Professor Kakalios, for accepting our invitation. We're really happy to have you here, even on Zoom in Quito, in Universidad Francisco de Quito. And so, thank you everybody for coming. So, Professor James Kakalios is a Taylor Distinguished Professor at the University of Minnesota School of Physics and Astronomy. He did his PhD in physics from the University of Chicago in 1985, and he's author of a very popular science book that you probably know, The Physics of Superheroes. This talk will be about this book and about our comic book are very good physicists. So I will not take time. I'm sure that those will be very entertaining and funny. So I'm leaving you with Professor Kakalios. So thank you very much again. So we can start.
Thank you. Thank you very much. I'm very honored to be giving you a talk. I'm sorry that it can't be in person. I mentioned to my daughter that I was giving a talk in Ecuador, and she said, "Hey, do you need me to come along?" And unfortunately, I said, "No, it's going to be on Zoom, but maybe someday soon we'll all be together." So thank you again for inviting me. And I would like to talk to you about the uncanny physics of superhero comic books. As mentioned, I'm a professor at the School of Physics and Astronomy at the University of Minnesota. So let me begin by just describing how a mild-mannered physics professor became associated with Spider-Man and Superman. In my day job, I'm a condensed matter experimentalist. So experimentalist means that I work in a laboratory, and condensed matter is just a fancy way of saying solid state physics. My research actually goes from the nano to the neuro. We make amorphous materials, and we make nanocrystals of different semiconductors and embed them into the amorphous semiconductors in order to make new materials that have hopefully superior properties for solar cells or transistors. And I have other projects where I collaborate with professors in neuroscience, where we use techniques we developed to study electrical noise in disordered semiconductors and apply them to voltage fluctuations in the brain. But that's not why I'm here today. I'm here today because back in 2001, 20 years ago, wow, that's now starting to make me feel quite old. 20 years ago, I created a class at the University of Minnesota that was originally called Everything I Know About Science I Learned from Reading Comic Books, which my colleagues say explains a great deal. Now, this is a real physics class that covered everything from Isaac Newton to the transistor, but there was not an inclined plane or pulley in sight. Rather, all the examples came from superhero comic books, and as much as possible, those cases where the superheroes got their science right. I show here an old comic from the 1960s where Superman visited a college campus, university in Metropolis. And I bought this comic when I was a kid because I was very interested in what life in college was going to be like. And even as a kid, I knew that this part wasn't too accurate, but there were things about this that did turn out to be correct. Namely, all college professors at all times are 800-year-old white men, and all college professors always wear caps and gowns, as you well know. Well, the class was a success. And then in the spring of 2002, the first Spider-Man movie opened up. This is the one with directed by Sam Raimi, starring Tobey Maguire. And I thought this would be a good opportunity to get some science into the newspaper. So I wrote an essay about how the death of Spider-Man's girlfriend, Gwen Stacy, in, as you well know, Amazing Spider-Man number 121, turns out to be a textbook illustration of momentum and forces. And I sent this article to my local newspaper, the Minneapolis Star-Tribune, and they published this on the Friday that the Spider-Man movie was going to open. Now, and the University of Minnesota put out a little press release about this article and about my class, saying, well, Spider-Man is on the movie screen, But if you want to know about the science of superheroes, the person to ask is Professor Jim Kakalios, blah, blah, blah. The university has put out press releases about me before, about my research on nanocrystals or electronic noise. Result, zero. You write one story about Spider-Man, however, right? And so this came out on Friday. The movie opened on Friday. The press release went out on Friday. By Monday, there were calls from the BBC, CNN, all sorts of newspapers, the Associated Press contacted me, came to my office where I just happened to have these lecture demonstration tools on hand. That was a lucky blow. At this stage of my career, I realized that I could win 3 Nobel Prizes, and I know what photo they're using in my obituary. I say, win 3 Nobel Prizes, and my colleagues say, how? In a dice game? But this article actually went around the country. I'm in Minneapolis in Minnesota, but here is a clipping from the Chicago newspaper that my sister-in-law sent me. And then it actually went around the world. So here is a clip from a newspaper in Turkey that one of the graduate students brought back, where I think I know what they're saying about me. And then I started showing up in places where physics professors don't usually show up. So during lockdown, if you're playing a card game, there's a game that's popular here in the US. Not sure, I don't know if you have it in Ecuador, Trivial Pursuit, where they have trivia questions and you get to ask each other, and whoever gets the most questions right wins. I'll tell you right now that if you're playing this game and you have volume 6 and you get card 291, I'll tell you that the science question is kryptons. The question was, what planet's gravity did science professor Jim Kakalios estimate by calculating the force needed to leap over an Earth building in a single bound? Now, I didn't even know about this. One of the students brought this to me. So I borrowed the card. I went down to the main physics office. I went to my department chairman. I showed him the card and I said, Alan, who's the most famous scientist you know? And he looked at the card and he looked at me and he said, Stephen Hawking. I said, well, who's not a genius? And he said, oh, well, then it's you. But the nice thing about all of this attention, this media attention, is not the media attention, but really the hundreds of emails that I received from students and teachers and people long out of school who liked this idea of using superheroes to teach physics and asked if I had a book, which eventually led to my writing a book, The Physics of Superheroes, which is in its 2nd edition now. And that was followed up by a book on the amazing story of quantum mechanics, which talks about how we were promised jetpacks and flying cars, but we got cell phones and laptop computers instead. And it's all quantum mechanics that led to this. And then finally, the most recent book was The Physics of Everyday Things, where I follow you throughout your day. And every time you interact with some technology, I explain how it works and the physics behind it. So let me show you some things about how you can look at the physics and of the superheroes. Now, I'm not going to try to explain how the superpowers work, because clearly that's physically impossible, right? And I don't see myself as going around and being like Dr. No or Professor Grumpy and say, well, this could never happen and this is impossible, and why don't the Hulk's pants fall off, and unstable molecules. So what I do is I grant each character a one-time miracle exemption from the laws of nature. Just like when you're solving a physics problem you might say, well, let's ignore friction right now, or let's ignore air resistance, or things like that. So here I say, well, let's assume that if you were super strong, or could stretch like a rubber band, or could run at super speed like the Flash here, could you run across the ocean or up the side of a building, drag people behind you in your wake? All things that the character is shown doing using his super speed, all things that are correct from a physics point of view once you make that suspension of disbelief. So here's the Flash, a DC comic superhero who has the ability to run at super speed. He can run super fast, and a crook is shooting at him, but the Flash is faster than a speeding bullet, so that's not a problem. But there are innocent bystanders in the way. And the Flash is not super strong. He's not bulletproof. He's just very fast. But we see here in the next panel, whoops, with a sweeping motion, the Flash plucked them, the bullets, right out of the air before they could harm him. And then there's an explanation saying Flash's action in stopping the bullets is similar to that of a baseball fielder who stops a hot grounder by letting his glove travel momentarily in the same direction as the ball. I mean, this is actually correct. This is, if you had super speed, how you would stop a speeding bullet. I, over the summer, picked up an object that was going 600 miles per hour. When I had a drink of ginger ale on the airplane. Took an airplane trip over the summer and pour yourself a little drink, and it's going 600 miles per hour. I'm going 600 miles per hour, no problem. If I'm standing still and it's going 600 miles per hour, then I have a problem. So this is a correct use of the Flash's impossible super speed to talk about some very real physics. We can actually look at some more advanced topics. Here we see the Flash trying to run at the speed of light, and he's finding it somewhat difficult. And he's thinking, it's taking me a little longer than usual to reach light velocity. I wonder if I'm tired or something. That could affect my super speed. Good gosh, there's no doubt of it. I'm slowing down. I'm going slower and slower despite all my efforts. And then the Flash realizes, I can't go any faster because I'm getting heavier. Something's happening to me. And those of you who know Einstein's special theory of relativity know exactly why the Flash is gaining mass as he tries to run at the speed of light. An alien is shooting him with a gravity increasing ray. But if you take it out of context, it's a beautiful illustration of Einstein's principle. One last example with the Flash. I just love this one because it's kind of so silly. In this story, something has happened to the Flash so that he can't touch anyone or anything without killing them. Okay, don't ask. It's comic books. And the Flash wants to stop a bank robber, but he doesn't want to kill him. He just wants to capture him and hand him off to the police. So he does some creative problem solving. He runs a half mile away and he starts racing around a pear tree. And he's thinking, by setting up a current of air, I've shaken those pears off their branches. Now by racing swiftly back to the car, I'll start a suction to draw the pears after me. And then he says, I'll duck down and the pears traveling at high speed will do my job for me, thereby illustrating Newton's third law of motion, which is usually referred to as, for every action, there is a reaction. But also another way to say it is that forces come in pairs. Okay, pairs, not pairs. Okay. Even though this is over Zoom and you're all muted right now, I could still hear you groaning at that bad joke. But I have to remind you that I am a teacher. Therefore, your hatred only makes me stronger. Okay, so the superheroes and physics in the 1960s had one thing in common. a lot of white men. In physics, there is a growing effort to expand the talent pool in all of the fields, what we call STEM, science, technology, engineering, mathematics. And we want to get as many different people as possible to contribute. And in addition to wanting to do this just because it is the right thing to do, with the problems we have to face going forward, we need all the talent we can get. And here I have to say that comic books have been ahead of the curve. If you look right now there was a series where Captain America was Sam Wilson. Thor was Jane Foster. The Hulk was Amadeus Cho. Iron Man was Riri Williams. The Blue Beetle was Jaime Reyes. Ms. Marvel, Kamala Khan. Spider-Man, Miles Morales. And there's, of course, the unbeatable Squirrel Girl. I love the unbeatable Squirrel Girl. She has all the powers of a squirrel and all the powers of a girl. And in the comic book series that she was a college student that was studying computer science. And she would be shown going to her computer science lectures and learning something, and then she would use that information when she was fighting some sort of bad guy. And it was a great, fun comic. And I wrote to them and I said, you know, the only thing is, you only show her going to computer science classes. And people in college, especially freshmen, in the first year, like Doreen Green was, the Squirrel Girl, they take other classes. They take physics, they take math, they take, English, or literature. And so I wrote this, they published the letter, they said, yeah, that's a good point. And then I was interviewed for a website about the physics behind superhero punching. And Professor James Kakalios weighs in. And then a few months later in Squirrel Girl, she is trying to talk her friend into cutting the physics class. And they go into physics class and they see that today's lecture is going to be the physics of punches. And she says, offer rescinded. I forgot how physics is totally amazing. And I have to agree with Squirrel Girl. And I hope to show you this afternoon how totally amazing physics can be. So we have not just multicultural in the comic books, but also in the movies are finally catching up. We have, there's a obviously very popular movie, Black Panther. We've had Captain Marvel, Carol Danvers, and we've had, of course, Diana Prince, Wonder Woman. And Wonder Woman, this gives us an opportunity to talk about some real physics and her bracelets. So Wonder Woman is not herself bulletproof, but she's got very strong bracelets and she uses them to deflect the bullets. So we saw this in the Wonder Woman movies. Well, what we can ask ourselves, how strong do those bracelets have to be? Okay. She uses her Amazonian reflexes and strength, and she deflects the bullets, but that's of course assuming that the bullets ricochet from the bracelets in the first place. And in the comic books, it is said that the bracelets are made of Amazonian metal. So let's see if we can figure out how strong Amazonian metal must be. Well, we use a simple equation in physics that the force times time, which is called the impulse, leads to a change in momentum. A bullet comes in with a certain amount of momentum and it ricochets and comes right back out with the same speed. So it has the opposite momentum. And so we can say if we want to deflect a 22 caliber bullet, which has a mass of about 0.02 kilograms, and if it's traveling at 300 meters per second, and if the time that it bounces is about 1 millisecond, a thousandth of a second, then the force that you have to supply to balance this equation is nearly 3,000 pounds. And of course, that's over the area of the bullet. So that gives you a pressure of about 70,000 pounds per square inch. Okay, so that's pretty high. And if you could ask what metal can withstand this pressure, pretty much all of them. You go look up the properties of metals, and you see that most high-strength steels can withstand over 75,000 pounds per square inch. So apparently Amazonian metal is nothing more exotic than cold rolled steel. Okay, so I just need to stress one more time, it's a good thing that she's on our side. Okay, now I want to turn to Spider-Man and talk about some of his abilities and powers. Spider-Man, as you know, created in 1962 by Stan Lee and Steve Ditko, about Peter Parker, a high school student who was bitten by a radioactive spider, does not get radiation poisoning and die, but rather gains a set of fantastic abilities with which he fights crime as the Amazing Spider-Man. Two of the things that Spider-Man can do, I want to focus on this afternoon, his wall crawling and his web swinging. So let's look at wall crawling first. And we have Spider-Man, and he can cling to surfaces and walk across walls or ceilings. And you know, this is not so crazy because gecko lizards are able to climb up walls and walk across ceilings. And if you ask, how does a gecko lizard do it? They use just static electricity. The gecko lizard, if you look at their feet and you zoom in, you look at these little pads and you find that you have millions of microscopic fibers in each of these little pads. And these fibers cling to the wall due to electricity. Now, the gecko lizard doesn't like drag its feet across a carpet in order to build up a static electricity charge. What the gecko lizard uses is what something called the van der Waals attraction, a very weak but definite attractive force. So if you have a fiber, like in the gecko lizard's foot, and here's the wall, when you bring the fiber very close to the wall, there are fluctuations in the electric charge, and they induce opposite charges in the wall. Because if a region is more negative, it makes the region near the wall, it attracts more positive to the wall. And if there's a region that's more positive in the fiber, it pulls in some more electrons in the wall. And the negative and positives and negatives attract each other. Now, these are not static charges, these are fluctuating charges. So this force is very weak. So if you increase the distance by a factor of 10, the force goes down by a factor of 1,000,000. So this is why the fibers have to be microscopic, so that the surface area to volume ratio is large enough that you can get very close to the wall. And this is why you need millions of them, because the force is very weak. So you need to have many of those fibers in order to be strong enough to hold on to the wall. This is how a gecko lizard does it. I'm not sure how Spider-Man does it, but this is how someday we may be able to do it. Because scientists are making artificial gecko tape. they are making arrays of microfibers, and this image was actually in a paper that was published in Nature Materials. When they reported the development of gecko tape, they showed how good it was by having a Spider-Man action figure cling to a surface, and it's held up by the gecko tape that's not held up by glue. So there are many technical challenges that have to be overcome before this tape is able to hold up a person, as opposed to just a little toy action figure. But I make you now a promise that if this ever becomes as common as, say, Velcro, I'm never waiting for the elevator again. This side of the building. Okay, well, that's wall crawling. What about web swinging? Spider-Man in the comic books has a technological web shooter. He has created a special kind of adhesive, and he shoots it out through a device he wears on his wrist. And when it sticks, it's strong enough, and he swings around. And it's in fact actually very strong. And if it is anything like real spider silk, it would be very, very strong. Real spider silk, pound for pound, is stronger than steel cable and is stretchier than nylon. It does this by having thousands of rigid nanocrystals that provide the strength, and they're connected by polymers that can stretch, and that provides the elasticity, and the whole thing is in a tube that's filled with fluid that uniformly distributes the forces along the length of the fiber. Now, okay, I want to, but how strong actually is the spider silk? And to answer that question, we need to do an actual experiment where we stretch the fibers until they break. And to do that, fortunately, we can go back to the second of the Sam Raimi, Tobey Maguire Spider-Man movies and look at Spider-Man 2. Now, I'm having some trouble with this video. So what I'm going to do is I'm going to show it here. And hopefully this will work out. Yes. So Spider-Man is on a elevated train that is out of control, and he needs to stop it. And so he shoots all his webbing to the buildings. I see that look in class a lot. Okay. Let me go back to the PowerPoint. So how can we use that scene to figure out the strength of the webbing? Well, we can estimate the diameter of the webbing. We can count how many web lines he shot out to the buildings. We look up online the mass of an elevated train. We determine its initial velocity by looking at how long it takes it to pass a city block. We know the final velocity is 0 because he brings it to rest. We can then, by looking at how many blocks it goes past, figure out the distance over which the webbing stretches before stopping the train. And from all this, we conclude that the tensile strength of the webbing, how long it is that you can stretch it before it breaks, has to be about 1,000 megapascal, which is 145,000 pounds per square inch. Okay. We were talking about steel before that had a compressive strength of 70,000 pounds per square inch, because this is twice that amount. Steel has a tensile strength of 250 to 500 megapascals. Real spider silk has a strength of 1,200 megapascals. So it would be strong enough if his webbing is like real spider silk, which shows an important point. They couldn't put it in a movie if it wasn't true. Right? Remember that next time you go to the movies. Now, as strong as spider silk is, that is like nothing compared to a much stronger material, carbon nanotubes, which have a tensile strength of 60,000 megapascals. Okay, so I want to talk about that a little bit just now. Not all solids made of carbon are created equal. Okay, you have diamond. This is all carbon atoms, and they're arranged in a tetrahedral arrangement. Or you could have graphite, where the atoms are arranged in stacks, in layers, like a dessert pastry, where you have many layers of the dough. And instead of each atom being connected strongly to 4 other atoms, the atoms are connected very strongly with 3 other atoms and very weakly to the atoms above and below. And this is why we use graphite in pencils, because it makes it very convenient. When you are writing, you press down and you peel off the graphite, the carbon, layer by layer when you write with a pencil. Here is a scanning tunneling microscope image of the surface of graphite. Each one of these white dots is a single carbon atom, and we can see them arranged in this hexagonal pattern in this way. And as I said, this is why it's very good for pencil lead, and this is why you also use graphite as a lubricant very often, because it slides very easily. And if you could slide off one single sheet, it would have such special properties that we give it a special name. We call this graphene. And I will be talking more about graphene in a moment. The way you make graphene, one way to make graphene, is you take this the pencil lead, right? And you take some graphite, and then you take some Scotch tape and you put it on and you peel off some layers. And then you put some more, and you peel off some more, and some more, and more, and eventually you get to only one layer of carbon atoms, and then you've got graphene. And in fact, the first people to make graphene and study its properties made it exactly this way. And they got, in 2010, Andrei Geim and Konstantin Novoselov got the Nobel Prize in physics for doing this. So if you have a pencil and some tape at home, you have all the equipment you need to do Nobel Prize quality research. So no excuses. But if I take a sheet of graphene, and then if I roll it up into a cylinder, I have what's called a carbon nanotube. And this is only about a nanometer or 10 nanometers, across. This material, because the carbon atom, the bonds between the carbon atoms in the sheet of graphene are even stronger than the bonds between the carbon atoms in diamond. And so you roll this up into a cylinder and you have a material that's actually stronger than diamond. And in fact, if you could make a cable of these carbon nanotubes and you would braid them all together, and the cable was no larger than this little dot that you see here, it would be able to hold up 2 sport utility vehicles, 2 very large automobiles in this way, just this little fiber alone, because those bonds are extremely strong. Now, in the most recent Spider-Man movies with Tom Holland, we see him making in his high school chemistry class, because it's a comic book story, making his webbing. And we can see from his lab notebook that he's obviously getting some graphitic carbon used here. And it's good that he has that, because at one point in the movie, he has to actually hold a ferry boat together, which has been sliced in half, because of course it has. But this is extremely strong enough. And this part, the fact that he can hold it together using the webbing, is probably is the least realistic part of the scene. Excuse me. The problem has been, up until recently, that we can make small quantities of carbon nanotubes that we can study in the laboratory. But to make large amounts, like for Spider-Man's webbing, that was too hard. Up until recently, at the University of Cincinnati in Ohio, which is a few states over from me here in Minnesota, Professor Veselin Shanoff has been able to actually make large quantities of carbon nanotubes and braid them together into actual fibers. Here you see one of his students pulling this out, and it almost looks like spider webbing as they're pulling it out. But these are carbon nanotubes braided together, and he's been able to get at least one fiber that is 50 yards long, basically 50 meters long. 50 meters long. And you see here, pulling this out, and here's one of his students pulling this, and you can see extending out the carbon nanotubes. So whether we're going to have Spider-Man webbing at some point in the future, well, that we'll have to see. But real scientists are doing real research on things that up until recently had only been in the realm of comic books. I mentioned that I was going to get back to graphene. And so what happened here, graphene shows up in an issue of Iron Man back in 2014. And Iron Man, Tony Stark, has changed his Iron Man suit to look like something where he basically stepped out of the Apple store. I don't know, maybe that's why his name will be like that. But he's also changed his suit so that there's his face is no longer covered up with a plating, so that his adoring public can see his face. You know, I love you, Tony. However, leaving your face unguarded like this can have its downsides. Like when somebody who's angry at Tony Stark walks up to him and shoots him point blank in the face. The person who shot him is actually stunned to discover that he's not harmed. And Tony Stark explains, it's called graphene, stronger than most steels, transparent. Now, Graphene, since it's one atom thick, allows 97% of the light to pass right through it. So it would indeed be transparent. But is graphene actually bulletproof? And here I have so it is indeed strong and transparent. But the question is, so it's very strong, as I've mentioned. If you had a sheet of graphene, you have a sheet of paper and it just hangs down under its own weight. A sheet of graphene would be so strong that you could hold it out solid. And not only that, but you could have two people standing on the edge of this one atom thick sheet and it wouldn't deflect down and wouldn't bend. That's how strong and rigid the graphene is. But is it actually bulletproof? Okay. Well, that issue of Iron Man, where someone tries to shoot Tony Stark in the face and the graphene shield protects him, that issue came out in the same week when another magazine landed on my desk that had equally fantastic stories, Science Magazine. And we see here one of the articles that they promote on the front page is shooting bullets through graphene sheets. And this group of researchers down at Rice University, down in Houston, Texas, dynamic mechanical behavior of multi-layer graphene via supersonic projectile penetration. They took sheets of graphene and they shot little quartz bullets, little quartz pellets at the sheet. And they studied how much energy it takes for the bullet to go right through, to make a hole and go through, as opposed to get deflected out. And it turns out to be a lot. Here is the amount of energy it takes to penetrate a given amount of thickness of material. And here's steel, aluminum, and PMMA. And these are the materials down here. And as you have a faster and faster bullet, right, the energy that you come in is greater, but you can penetrate. But here is Kevlar. Kevlar is really good, bulletproof protection. Here is graphene. So it takes a lot more energy to go through graphene. What happens is, in this single sheet of graphene, the speed of sound is much faster than it is in regular solids. And so when you come in to try to penetrate the graphene, it sets up vibrations of the atoms. And since the speed of sound is so fast, that energy gets transmitted away from the point of impact faster than the impact could break the bonds and penetrate through the graphene. So the graphene resists breaking those carbon bonds and maintains its integrity. So the fact that in the same week, we got a comic book with Iron Man and graphene, and we got a science article with bulletproof graphene was too good a coincidence for me to pass up. So I wrote an article for Wired.com that was called "The Magic Bulletproof Material That Made Iron Man Give Up Iron." And it basically gave me an excuse to write an article about graphene and how amazing graphene is. And there were these comments, of course, at the end of the article. Usually people say, never read the comments. But there was actually a great comment from someone who asked, what's protecting his hair then, right? Because his hair was also exposed. And before I could log on and give an answer, somebody provided the perfect response. Someone else answered, Brill cream, stopping bullets since 1928. Brill cream was this greasy stuff that people used to put on their hair back in the 1950s, and you put enough of it on and your hair was pretty much bulletproof. So anyway, I thought that was a good illustration of creative problem solving. Let's see, how am I doing? Great. So what determines the strength of materials? Well, basically chemistry and geometry. Chemistry, what is the material made of? How are the atoms held together? That we talked about, say, with carbon nanotubes. We talked about that with graphene. But geometry also plays an important role. So I can illustrate this in the last few minutes by talking about Gormu and the square cube law. So back in the 1980s, there was an issue of Fantastic Four that told the story about before the Fantastic Four got their powers by being exposed to cosmic rays, and again, not dying due to radiation, but being able to have all sorts of Fantastic Four powers. There was a comic where Gormu was attacking the Earth, and the scientist Reed Richards had to stop them. Now, this was in the 1980s, and this issue was actually paying tribute to the comic books that Marvel Comics used to put out before they were publishing superhero comics. They used to publish giant monster comics. They would have Tales to Astonish or Journey into Mystery. And here's like, I Challenge Groot, the monster from Planet X. This is the same Groot from Guardians of the Galaxy. And when he first appeared in comic books, he was trying to take over the Earth. And he had a little bit more of a vocabulary than he has in Guardians of the Galaxy. And this happened every month with some sort of giant monster. And the police couldn't stop them. The army couldn't stop them. And Earth would be doomed if not for the efforts of one lone scientist who would always figure out the one weakness that these invaders had. And it was always something different. And so this was Tales to Astonish number 13 that came out in 1962. And this is the very last panel in this story where the sheriff, when he realizes what Evans, the scientist's plan is to stop Groot, says, well, I never even thought of that. And a townsperson says, that's why Evans is a scientist and you're only a sheriff. And Evans' wife hugs him and says, oh, darling, forgive me. I've been such a fool. I'll never complain about you again. Never. And personally, I can't tell you how often I hear that in my own household. I can't tell you because it involves imaginary numbers. But it's a good thing that these scientists were on the case. Because if they didn't have to deal with Groot, they had to contend with Lokar or Orgo or Mumba or Rambu or Gruto or Brutu or Gugam, son of Goom, or Fin Fang Foom, all of which pale against the most terrifying monster of all, the tax collector from outer space. Well, getting back to Gormu, in this issue of Fantastic Four, Gormu's advantage in trying to take over the Earth is that if you struck him with any type of energy or projectile, so you shot him with a bullet or a cannon shell, or you blasted him with some sort of energy ray, he got bigger. And so every time you hit him, he got it bigger. How do you fight someone like that? And initially, it looked like no one could stop Gormu. But then the scientist, Reed Richards, he has an idea. And he goes and he does a measurement and he confirms his idea. And he realizes that the only way to stop Gormu is to continuously bombard him with an energy beam. And at first, Gormu thinks that it is a weapon directed against me. But he says, no, not a weapon, a power beam. Yes, yes, give me more power. It gets bigger and bigger. But he says, but wait, something is wrong. The power surges within me, but I do not grow stronger. I grow weaker. I'm almost as big as the planet, yet I do no damage. It is as if I am no more than a phantom. What is happening to me? I am defeated. No. What Reed Richards realized was that Gormu was growing at constant mass, not constant density. So he got bigger, his volume increased, but his mass stayed the same. And he realized that he had this idea, and he tested it with the ruler when he realized that Gormu's footprints were getting bigger, but they were not getting deeper. And so that implied that the pressure was not increasing. And he realized he was gaining size, but not gaining mass or weight. He was just inflating. Now Gormu, the infinite monster, has become truly infinite. And of course, Sue Storm, his girlfriend, says, "Oh, Reed, darling, I'll never doubt you again." But this is a real aspect of the strength of materials. Density is the mass divided by volume. So we could say that the mass is the density times volume. And if you increase the volume, if the mass increases and the volume increases at the same rate, the density would stay the same. But if you make something, say, 3 times bigger, it becomes 3 times taller, but 3 times wider and 3 times deeper. So 3 times bigger means 27 times more volume, which if it increased at constant density means that the mass has to go up as 27 too. Okay, so what? Well, the strength of materials, like your muscles and your bones, don't depend on the volume. Their strength is determined by the area. So that if you increase everything by a factor of 3, the cross section increases by only 9. But you increased and became 27 times heavier. And so what happens is that, one way to think about this is if you want to hold up, you have a line that is strong enough to hold 20 pounds, and you want to hold up a 40-pound fish, you need to get another line. You don't get a longer line, you get a fatter line to hold it up. And this principle of the cube square law was in Squirrel Girl's physics class. He said, put it another way, here's the physics professor, who I think looks rather handsome here, I must say. Make yourself 10 times larger, your muscles get 100 times as big, but you have to carry 1,000 times more weight. That's why elephants look like elephants and not like giant mice. They have to be built differently in order to have that larger mass. I drew them for you because I am a good professor. Well, being a good professor, I know it is important to not run over my time. And so I will stop right here and thank you all, and just remind you that with physics comes both great power and also great responsibility. Thank you all very much.
Yeah, thank you very much for the talk. It was amazing. So let's see if we have questions now. Who wants
Sure,
to go
happy
first?
to take any questions.
Question? Let's see if we have a question. No, just someone saying it is excellent. No, don't be shy. Pablo, go ahead. Pablo, maybe you want to.
Hello, James. If I may call you James.
You may indeed.
Okay, Dr. Buchanan. Well, more of a question. I just want to say thank you. Right, your work has inspired me. I teach high school physics, and now I know that whenever I'm out of ideas, I just have to look up to you, and I'll have more than enough. So thank you so much. It was so interesting. I enjoyed your talk very much. It was beautiful.
Thank you very much. I should point out, you could probably find it somewhere on Amazon, in the realm of shameless plugs, that my book has been translated into Spanish. So it's out there somewhere. I only have right now next to me the English copy, but I do have in my house the Spanish copy as well, but I don't have it right here to show you. But so anyway, but thank you very much. That was very sweet. That's very kind.
Okay. So let's see. Apparently, nobody. Alessandro. Go ahead.
Oh, someone has raised their hand. Yep.
Someone is raising. Oh, yeah. So just unmute yourself at that.
Yeah.
If you.
Hello, can you hear me?
I can hear you. Yes.
All right, thanks a lot, Jim, right? Or James?
Yep. Jim, James,
Jim.
either way,
Thank you.
fine.
Yeah, thanks for the talk.
Thank
I
you.
actually have to confess that I have stolen some of your material for a couple of talks, trying to reach out to some students.
That's fine.
I am sure I fail completely, but once in a while I get across someone reminding me about, oh, you know, I learned this from this talk, or this is all they remember. So it's good material. I was just wondering about your course, right?
Mm-hmm.
What is the audience at your university? I'm sure I can figure it out and find out more. But I was wondering because, for instance, we have here some courses for non-physicists, of course, and people who actually need physics in their jobs, like for instance, doctors, right? If they want to use that technology. And even though it is really fun to teach through these examples and characters, at some point they have to become serious, right? So how do you balance this, and what's your experience about this kind of stuff?
That is an excellent point. You're absolutely right. When I first created this was a very special class that was only open to new first-year students, and that was meant to be open to anyone across the university. So I would have art majors and I would have chemical engineering majors. And so I had the students basically, instead of taking an exam, we would talk about the physics, we talk about the superheroes as illustrations, and then I'd have them to get a grade, they would have to make a presentation and they would analyze a certain scene from a movie or a comic book and analyze the physics behind it. And so that way, if they were chemical engineering majors, they could be very mathematical. And if they were art majors, they could be less mathematical. But you're absolutely right. So I don't actually teach that class. That was 20 years ago. I don't teach that still now, but I do bring in, when I teach my regular physics class, I do bring in superheroes every now and then, but I don't do it all the time. I tried to do it once on an exam, and instead of having a motorcycle catch up to a truck, and it was one of these standard problems, I had a rocket ship and the Flash, and I realized that doesn't work, because if you make a mistake with the motorcycle and the truck, and you calculate that the motorcycle has to be going 300 miles per hour in order to catch up to the truck, you say, oh, I did something wrong. This can't possibly be right. But if you calculate that the Flash has to be running 300 miles per hour, you say, yeah, well, could be. So it's not as good. So I think what happens you're absolutely right that in these classes where it is important that they also understand the seriousness, that sometimes, so that you can use a little bit of the superheroes, like little seasoning when you're cooking, and you add a little bit to add a little spice, but you don't want to put too much, because then all you taste is the spice. And the other thing that's good about the superheroes is when I'm talking to people who are not students at all when I talk to people just in the general public, because there are people who are interested in physics, but they're also very insecure. They're nervous that they're not going to understand what I'm talking about. And if you start talking to them about graphene and carbon bonds, they go, I can't get this. But if you start talking to them about Iron Man or Spider-Man, they don't get nervous right away. They will follow you and go along with it. And then, and if you can tie it to some sort of story or some sort of narrative, they have a better chance of understanding it. And I try to bring in things like that people are doing research in, not my research, but I look at what other people throughout the world basically are doing. And I get to report on that and to tell people about it, to kind of show them that there's a lot of interesting stuff that's going on that does affect their everyday lives. The things, the stuff that shows up in the newspapers is often things like, discovery of the Higgs boson or colliding black holes, and they create gravity waves, and that's been detected. And that stuff is fascinating. And that stuff deserves the Nobel Prizes, and they deserve the attention. But if that is the only thing that the public ever sees about science, they think that it has nothing to do with their lives. And a lot of times you ask people about scientific research and they say, what? No, something medicine, maybe, and wait a second, I'll look it up on my phone. And meanwhile, they're using all sorts of quantum mechanics, all sorts of technology that came about by basic research in order to do that. But they don't think about that. They think about, it was made by Steve Jobs, where Jobs really just figured out that he wanted the corners to be round. So in some sense, it's a good way to just try to, but it doesn't have to be superheroes. I have friends who do the physics of car races. I have friends who do, the physics of Star Wars or other things. Anything that you have, I know some people who do the physics of cooking. So it's just like taking something that people are already interested in and then using it to bring them over and describe some physics. Because they come home from work, they're tired, they don't want to hear a lecture. So if you can make it entertaining, if you can make it interesting, if you can tie it to something they're already interested in, well, then you've got an advantage.
Thank you.
Thank you.
I have a question. Well, actually, it's more like a comment and a curiosity. The comment is that when I read your book, I'm Alessandro, professor of physics here at the USP. What I liked the most when you calculated the gravity of krypton was not just the calculation of the acceleration of gravity, but the fact that you use it to conjure an hypothesis of why krypton was collapsing, as it did in the comic book. This was fantastic because honestly, it's kind of the way physics works. No, is you make a calculation, you extract an information, and then you can make an hypothesis. And that, well, actually, you should do additional research. But it was already fantastic. It's an example I use all the time to tell people how the physics work. The curiosity is this one. Why did you use the second law of Newton instead of energy? It would have been easier, maybe.
So what I was using there was I was using a simple example. This was calculating if you jump, what must your liftoff velocity be so that you could leap over a tall building? And that to get that velocity, you have to push against the ground with a force. And you calculate how much the force must be. And I use a simple expression, but I'm trying to show a reader who's not a scientist and doesn't know any mathematics, how they might reason through and get an answer. And I used, in the first edition of the book, I made a big simplification in order to get the expression. And I got a certain value for how much force it would take. And I then concluded that the gravity of Krypton had to be 15 times bigger than Earth. 15. And people would write to me after that first one and say, no. I did the calculation and it has to be like 150 times. And this is why, and this is why. And so I said, yes, this is true. But given I made the assumption that he's pressing down against the ground and he jumps in 1/4 of a second. This is the force. And one person wrote back to me and said, no, that's not right. That's not right. It's just not realistic that the time would be that long. And I wrote, we're talking about the last son of Krypton, able to leap tall buildings in a single bound and bend steel in his bare hands. And the part you find unrealistic is how much more time he spends pressing against the ground. And the person wrote back, said, fair point. I think I need to go outside and take a walk. And so, but in the second edition of the book, I was able to describe this conversation and point out how it would be actually the gravity of Krypton is probably 150 times. But I like the 15 because if I tell you that the gravity of Krypton has to be 150 times more larger than Earth, and I say, you can't make a planet that big, you say, yeah, that sounds too big. That's probably, yeah, that's right. But if I tell you that you can't make a planet just 15 times bigger and have it be a planet like Earth, you say, really? That sounds like I should be able to do that. But then you get to describe things like the density of materials and how the formation of the planets. And so that gets you into a whole different realm. Remember, my point is at the end of the day is not to try to prove that what we see in the comic books is 100% accurate, because I have some bad news for you if that's what you think, because the answer is it's just not real. But I'd rather to use the interest in trying to understand this to explain various physics principles. And if I can get to the end and show you that, say, if you made a planet with this much gravity, it would be unstable and hard to keep exploding, which is exactly what Krypton did, then you are so pleasantly surprised to find that something is correct in a comic book that it's like, it's like an aha moment. And again, the nervousness is dropped. And when the shields are down, you can try to teach them something.
Thank you.
Thank you.
Okay. So there is another question, Wagner from Zoom. So Wagner, you can unmute yourself and ask your question.
Hi. First I want to say thank you for your talk. It was very interesting.
Thank you.
And I also saw your video on YouTube on Insider about your iconic science in Marvel. You analyzing Marvel's.
Yes.
Yeah. I like that too. My question was about that. Have you ever been inspired by some comic or some superhero ability to do your research or your investigation? Like you saw you read a comic and then, oh, that can help me to do research.
Well, I haven't been actually inspired, but there was something that was kind of like almost that came out of a comic book. I said at the very beginning of my talk that we had put nanocrystals of one type of semiconductor into an amorphous, disordered other type of semiconductor in order to get new properties and try to study them for different applications. And we had put silicon nanocrystals in amorphous silicon, disordered silicon. And I was talking to a colleague who works at the Large Hadron Collider out at CERN in Geneva, Switzerland. And he thought that this material might be useful for particle detectors. And one of the things that you have to worry about with particle detectors is, can they function even when exposed to radiation? Because there's all these high energy protons that are flying around inside the particle inside the Large Hadron Collider. So we made some of these materials and we went down to a research reactor down in Florida, and we exposed them to radiation. We measured their resistance before, and we wanted to see, did the resistance, usually the materials become worse and the resistance increases. Your best case would be the resistance stays the same, in which case it's not affected by the radiation. What we found was that the resistance didn't go up, it didn't stay the same, the resistance went lower. And not only did the resistance went lower, but it was a permanent improvement in the ability of the material to carry current. And we published a paper and we're trying to understand what's going on. I'm trying to get some funding to continue these studies, but having something that becomes stronger when you expose it to radiation, oh, baby, can I talk about that and tie it into that I could justify all those comic books that I have down in the basement now. So I do have, that's not necessarily something that was necessarily inspired by the comics, but it has a very amusing connection to it in that way.
Yeah, thanks.
Other questions? Yeah. Time for a couple more. Let's see. In the room, Nacho. Nacho, go ahead.
First of all, thank you for your meeting. And I have a question about what happens to the heroes that get smaller and smaller and smaller, and to a point that you can see them.
I'm sorry, I had trouble hearing that. I heard.
I have a question.
Yeah.
About what happens to the superheroes that get smaller and smaller,
What happens to the superheroes when what? I'm sorry.
That gets smaller.
Oh, when they get smaller. Oh, yeah, that's a good question. Okay, so there are a lot of superheroes that can shrink. You're right. Absolutely. And how do they do this? Right? The atoms in your body are already touching each other. And if you try to get them closer still, you would need such enormous pressures that you would be just destroyed. you can't take atoms out because where are you going to put them and how you get them back when you want to go back to full size? The only way that I thought about this, and this is not my idea, this came from a novel by Isaac Asimov, Fantastic Voyage 2. And when you say, what determines the size of an atom? Well, it's quantum mechanics, but basically you can calculate in quantum mechanics how big an atom is. And it is a connection, it involves an arrangement of different fundamental constants: the charge of the electron, the mass of the electron, the what's a number that's called Planck's constant. Now, all of these constants have one thing in common. They're constant. They don't change, which means the size of the atom is fixed. But if you allow me to figure out some way to change the value of these constants, if I could change Planck's constant by a factor of 10, the atoms would get 100 times smaller. And if all the atoms get smaller, they could still be together. You still have the same number of atoms, but now you are a much smaller person. Now, we have no way to, we don't know how to change constants of nature. It would be useful if we could figure out how to, say, change the speed of light or the mass of an atom or something, make it lighter so you can easily pick it up and move it over to another place. So we don't know how to do this at all. But the fun thing about this is it gets you into thinking about things that you wouldn't ordinarily think about, like what determines the size of an atom, and gets you into thinking of how you might adjust something or change something to fit in with to explain what you see in the comic books. Obviously, the stuff in the comic books is not real, but it's fun sometimes to think about this, and it gives you a better feeling for the basic physics that underlies what's going on.
Thank you so much.
Thank you.
Thank you, Nato. Other questions?
Well, I want to thank you.
Yeah.
This has been a lot of fun. I'm, like I say, when I said that I wish I could be there in person. Melissa in the chat said next time. So Melissa,
Exactly.
I'm gonna hold you to that. I'm gonna hold you to that.
No, and you know, in your biography, I read that you moved from California because you were like bored about the bored winter. So apparently in Minnesota they are boring. So I just want to tell you that here the weather is very boring. It's always a warm spring. So now,
you know,
I'm so sorry. So yeah, it's very boring.
So do not have me out in October. You asked me out in January. That's what.
Okay. So no problem at all. So it's I didn't say just for sake. No, I was serious about it. So we will be happy to have you here. And I'm sure that you have many more things to tell us about.
Oh, so, absolutely. I got a million of them.
And congratulations on your tie. It's really cool. Yeah. Yeah. That's so good that I could, because now we can see also that.
You know, I bought this tie a long time ago, before the books, before the show, just because I'm a nerd and I like comic books. And I never thought I'd have so many reasons to wear it for professional reasons.
So it's a very nerdy and beautiful tie. Congratulations again. So thank you very much for sharing this time with us. So next time it will be here in Quito with our very boring spring.
I love it. Thank you again. Thank you. Have a great rest of the week. And keep reading those comic books.